Hello everybody. So we begin here the next session of our lecture series on vector algebra. So in the last class we had talked about multiplication of vector by a scalar, and today we will progress with multiplication or product of two vectors. Now if we think of product of two vectors, actually it can be defined in two different ways. These are two well-known products. One is the dot product and the other is the cross product. Now dot product is actually the product of two vectors where the resultant is a scalar quantity. So it's also called the scalar product. Whereas cross product is the product where the resultant is a vector quantity, and hence we call it also vector product. So we will see them one by one, and we will start today's lecture with the dot product or scalar product. And we may think that why do we need the two kinds of products, and why two vectors are giving a scalar. But these definitions are actually motivated by physical or real life applications, which we will discuss little later after defining the scalar product or dot product. So what is the dot product or scalar product? For any two non-zero vectors a and b, it is defined by this equation. We denote the dot product as a dot b, and it is given by mod a multiplied with mod b multiplied with cosine theta, where theta is the angle between the two vectors a and b. So once again, if we revisit the definition, the dot product is the product of the magnitude of the two vectors multiplied with cosine of the angle between the two vectors a and b. Like if we have here two vectors a and b and theta is the angle, then we get here this cos theta. And mind it, we actually take the smallest angle. Here also there's actually this a and b, there's another angle over here, but we take the smallest angle. Now one thing, we have defined this dot product for non-zero vectors. What about if we had zero vectors, if one or both the vectors were zero? Can we define the scalar product then? Now actually, if one of them is zero, if a is zero or b is zero, it happens what that we cannot draw that vector. Say if a is 0, it's a vector of length 0, so we cannot actually draw, and therefore theta becomes undefined. So that is why in our definition we had this term that non-zero vectors. So how do you define the dot product for zero vectors? So if any of the vectors are 0, then we just define the dot product as 0 only. We just say that a dot b will give us 0. Okay, so now from this definition, we will make few observations. And the first observation here is that a dot b is a real number. I hope that we have understood this very clearly from the definition, because mod a, mod b, these are the lengths of the vectors, real numbers, and cosine theta, this is also a real number. There is no vector associated in the right hand side. So very clearly a dot b is a real number. Okay, so our next property or the observation basically, that if in case we have two non-zero vectors, can a dot b be 0? Please recapitulate that we have told that if either a is 0 or b is 0, then we define a dot b is 0. So now the question is that if a and b are both non-zero, in that case can it happen that a dot b is 0? Let us think when it can happen. It can happen only when cos theta is 0. And when cos theta is 0, of course, when theta is 90 degree, that means a dot b equal to 0, this can happen if a and b are perpendicular vectors. So this is what is denoted here, that a dot b equal to 0 implies both ways if and only if A is perpendicular to B. So this is a very important observation or result when we talk about scalar product. Now the third one, in case theta is 0, that means both are collinear vectors basically. In that case, theta 0 means cos 0 is 1. So A dot B is simply the product of the magnitude of the two vectors. And in particular, if B is equal to A, so A dot A is mod A whole square. That means the square of the magnitude. And similarly, if theta is pi, 180 degree, then cos theta is minus 1. So A dot B will be minus mod A mod B, and A dot A in this case will be minus mod A square. Now, using some of these observations, we now have some more important result. That is that if we think of the unit vectors along the x, y, z directions, that means I, j, k. This notation we had introduced in the previous session lecture. I hope you remember. I, j, k denote the unit vectors along the 3 coordinate axis, and of course they are mutually perpendicular vectors. Then we have this two again very important relation, I dot I equal to j dot j equal to k dot k equal to 1. From where do we get it? If we go back to the previous slide again, here we see that A, dot product of a vector with itself, that is square of the magnitude. Now because these are unit vectors, so obviously the dot product is 1. And if it's I dot j, that means we are perpendicular vectors. You remember that for perpendicular vectors, the dot product is 0. So I dot j, j dot k, k dot I, all these products are equal to 0. So once again, I repeat, in view of this scalar product, these two are very, very important results. And the last observation over here, that because our definition of the scalar product gave us A dot B equal to mod A mod B cos theta. So from that definition directly we can get cos theta equal to A dot B by mod A mod B, or therefore the angle between the vectors can be calculated from this formula, theta equal to cos inverse A dot B by mod A mod B. Okay, so with these observations we continue with some more properties of scalar product, basically some laws, very important laws. The first one is the commutative law. Scalar product, once again, like vector addition, multiplication by a scalar, it satisfies the commutative law. So for any two vectors A and B, A dot B is equal to B dot A. Now that is also very obvious if we remember the definition, because A dot B would have been mod A mod B cos theta, and B dot A will be mod B mod A cos theta. Now obviously mod A mod B equal to mod B mod A, because these are nothing but real numbers. So A dot B is also equal to B dot A. Now the second property is distributive law. So now if we have three vectors ABC, then A dot B plus C equal to A dot B plus A dot C. So this is the distributive property of multiplication over addition basically. So if we have three vectors, if we add B plus C first and then calculate the dot product, that is same as if we have calculated the individual dot products A dot B and A dot C and then added, they are the same. This also can be verified very easily. And the third property is associative property, associativity with scalar. So lambda A dot B, rather lambda A dot B, that is equal to A dot lambda B equal to lambda A dot B, where lambda is the scalar. So therefore we can see that we can again just play around with the brackets. We can just change the positions without affecting the result. So with this, the properties are over. Now we will see another very important thing, scalar product in component form. Now this representation of a vector in component form, this was also discussed in our previous session lecture. So if a vector OP, say, represents the position vector of a point P whose coordinates are x, y, z, we remember then that this vector OP is having the scalar components x, y, z, or it can be represented as xi plus yj plus zk. So now here suppose we have two vectors a and b which are written in the component form as a1i plus a2j plus a3k, and the second one b is written as b1i plus b2j plus b3k. Then their scalar product, just we go via the definition, a dot b will be this a1i plus a2j plus a3k dot b1i plus b2j plus b3k. But now what will be the result of this dot product? If we look into this little bit carefully, we can easily get the answer, find the answer on our own. See, first, of course, we will multiply term by term. So a1i dot b1i. So the product is a1 b1. And what was I dot I? We have seen just now. So this was nothing but a1 b1. I dot I is 1. Now next term would have been a1 b2 I dot j. But what is I dot j? For perpendicular vectors, the dot product is 0. So I dot j is 0. So this term vanishes. Similarly, the next term will have I dot k. So this will also vanish. So from the multiplication by this first term a1i, we will be left only with a1 b1. And now if we go to the second term, a2j, so a2j multiplied with b1i, again this will give you 0 because j and I are perpendicular vectors. Mind it once again that whenever we will have perpendicular vectors, the dot product will be 0. Whenever we will have same vectors, dot product will be 1. So therefore only j dot j will give you a2 b2, and similarly now I hope we can understand when we multiply with the third component, only this k dot k will give you the coefficient a3 b3. So finally I hope we have understood the answer or the result for your dot product in the component form is a1 b1 plus a2 b2 plus a3 b3. So once again a very important as well as useful result. So when we have two vectors a and b given by a1i plus a2j plus a3k and b given by b1i plus b2j plus b3k, a dot b is going to be a1 b1 plus a2 b2 plus a3 b3. Very important result which will be very much useful in your subsequent studies also. Okay, and now before we conclude this scalar product or dot product, we will see the application of this scalar product in some very important aspect. So for that, let us look into projection of a vector on a line. What do we mean by that? Say we have here 4 figures. Let us look into one only. We have a vector A represented by AB, and we have here a line L, and the angle between the line and the vector A is theta, shown and in the anti-clockwise direction. So actually this projection means we will drop a perpendicular from this terminal point of the vector from B to the line L, and then this portion AC, this is actually the projection of the vector AB on the line L. If we think of it as a vector AC or denoted by this P notation, we will call this as the projection vector, and just the length AC is called the projection of the vector AB on the line L. And what is this projection? What is the length AC? If we apply our knowledge of trigonometry, this is a right angle triangle, this is the base and this is the hypotenuse. So therefore AC is of course mod AB or mod A cos theta. So this is your projection of the vector A on the line L. And if we look into the vector if we look into the thing as a vector, so this vector is of course along the line L, but the direction matters depending on the value of cos theta, whether cos theta is positive or negative. If cos theta is positive, then the direction of the projection vector is along L, and if it is negative, like we come to the figure 2 now, in that case the direction of the projection vector will be opposite to L. So here we can see that theta is greater than 90 degrees. It's in the second quadrant. So cos theta is negative. And what is happening now, if we have drawn a perpendicular from here, so of course this AC, it is directing towards the negative x-axis, or rather it is, in this situation I can say it is an opposite vector to L, oppositely directed to L. If we look into 3 and 4, we will also see the same scenario. So therefore, if we have the vector A, then AC is the projection of the vector on this line. And now, so this projection, what is the value of the projection then, or the magnitude of this projection? That is mod A cos theta. And if we remember now, our dot product A dot B is mod A mod B cos theta. So then of course I can write this as A dot B by mod B. Can't we? We can write this projection of a vector A on another vector B as A dot B by mod B. Or in other words, see, A dot B unit vector. So this is again a very important result, that the projection of a vector A on another vector B can be given by the dot product divided by the vector B, or rather A dot unit vector in the direction of B. Okay, so with this we are actually over with the scalar product. Next comes the vector product, that we will take up in the next lecture session. So we will close today. So goodbye till now.